In three-dimensional space, there is a familiar way to organize a Cartesian coordinate system. We begin with three mutually perpendicular planes. The Cartesian planes, XOY, XOZ, and YOZ. Each plane carries a square lattice. Together, these three planes establish the three coordinate directions of ordinary space. But there is another remarkable arrangement of planes in three dimensions. Instead of three mutually perpendicular planes, consider four symmetry-equivalent planes, each carrying a triangular or hexagonal lattice. At first, four planes may seem excessive, but their symmetry reveals something beautiful. Each plane has a normal vector, and the four normal vectors point toward the four vertices of a regular tetrahedron. So, the geometry of the four planes is encoded by the geometry of a tetrahedron. Choose one of the planes as our reference plane. Its normal can be taken to point in one direction. The other three normals must then be arranged symmetrically around it. Every normal has unit length, and every pair of distinct normals makes exactly the same angle. Their dot products satisfy. The dot product of ni with nj is equal wit, 1/3, whenever I is different from j. Therefore, the angle between any two normals is theta equals arc cosine of -1/3, the familiar tetrahedral angle of approximately 109.47 degrees. There's another elegant property. Add all four normal vectors together, and the result is 0. n1 plus n2 plus n3 plus n4 is equal with 0. The four directions balance one another perfectly, and this is the important idea. The four planes are not four unrelated objects. They form one highly symmetric system. Each plane carries the same triangular lattice, and the six directions within one triangular lattice are related to directions in the other three. This arrangement is closely connected with the tetrahedral directions of the cubic lattice, and with the geometry underlying close-packed structures, such as the face-centered cubic and diamond lattices. Now we can ask the natural question: if this is what happens in three dimensions, what is the corresponding structure in four dimensions? In three dimensions, we found four special directions. In four dimensions, we will be looking for a new family of three-dimensional hyperplanes. And the question is no longer simply how many planes can pass through the origin. There are infinitely many. Instead, we are looking for something much more special, a highly symmetric family of hyperplanes whose geometry is tied to a four-dimensional lattice. That search will lead us first to the geometry of the 16-cell honeycomb, and ultimately to something even more surprising: 12 distinct directions in four-dimensional space. The four directions of the tetrahedral picture are about to become 12. And that is where the geometry of D4 begins to reveal itself. In three dimensions, our four special directions came from a regular tetrahedron. They were the normals to four symmetry-equivalent triangular lattice planes. So now we make the natural jump. What happens in four dimensions? Instead of planes through a point in three-dimensional space, we now consider three-dimensional hyperplanes through the origin of four-dimensional space. Mathematically, there are infinitely many of them. Every non-zero vector in four dimensions defines a normal direction, and therefore a hyperplane perpendicular to that direction. So simply counting hyperplanes is not the question. We are looking for a highly symmetric family, and the most natural place to look is the four-dimensional analog of the tetrahedron, the regular four-simplex. A regular four-simplex has 5 tetrahedral facets. Each facet has an outward normal. So just as the four faces of a tetrahedron give four directions in 3 dimensions, the 5 facets of a four-simplex give 5 directions in 4 dimensions. Let those 5 unit normals be N1, N2, N3, N4, and N5. Because of the complete symmetry of the regular 4-simplex, every pair of distinct normals has the same dot product. For normalized normals, Ni multiplied by Nj is equal with -1/4, and, just as in the tetrahedral case, the vectors balance perfectly. N1 plus N2 plus N3 plus N4 plus N5 is equal with 0, so the analogy is remarkably clean. In 3 dimensions, 4 tetrahedral normals. In 4 dimensions, 5 simplex normals. The pattern seems to be working, but now we have to be careful. These 5 directions are the natural simplex directions. They are the 4-dimensional analog of the 4 tetrahedral directions. But they are not yet the complete answer to our original geometric problem. There is another structure hiding in 4 dimensions. The D4 lattice has a remarkable collection of shortest non-zero vectors. There are 24 of them. They are the 24 roots of D4. And because opposite vectors define the same unoriented axis, 24 divided by 2 equals 12. So, the lattice provides another natural count, 12 unoriented directions, or, if orientation matters, 24 oriented directions. And now we have discovered something subtle. There are 2 different notions of direction in 4 dimensions. The regular 4-simplex gives us 5 simplex directions, while the lattice gives us 12 lattice directions. These are not competing answers to the same question. They arise from 2 different structures. The 5 directions belong to the simplex geometry. The 12 directions belong to the exceptional symmetry of the D4 lattice. And this distinction will become crucial. The 24 nearest neighbors of a D4 lattice point form the vertices of the regular 24 cell. Pair those vertices antipodally, and 12 axes emerge. These 12 axes will turn out to organize the families of 3-dimensional hyperplanes that we are looking for. So, our simple 3-dimensional analogy has led us somewhere unexpected. We started with 4 tetrahedral directions. The simplex analogy suggested 5. But the D4 lattice is telling us to look for 12. And the next question becomes the central question of this chapter. Why 12? Where do these 12 directions come from? How do they organize 4-dimensional space? And what geometric structure do they generate? To answer that, we need to stop looking at the simplex and look directly at the D4 lattice. That is where the 16-cell honeycomb begins to appear. We have seen 2 possible ways of thinking about directions in 4 dimensions. The regular 4-simplex gives us 5 highly symmetric directions. But the lattice has something different. It has 24 shortest non-zero vectors, 24 roots. And those roots form the vertices of a remarkable 4-dimensional polytopa, the 24 cell. But the 24 cell is not just an isolated object. The lattice provides the centers of a much larger structure, a structure that fills all of 4-dimensional space. It is the 16-cell honeycomb. Its Schlafly symbol is 3, 3, 4, 3. The notation encodes the structure recursively. The first 3 symbols, 3, 3, 4, describe the 16-cell itself. Its 3-dimensional cells are tetrahedra, and 4 tetrahedra meet around each edge. But the final symbol takes us from the polytopy to the honeycomb. It tells us how the 4-dimensional cells fit together around their triangular faces. So the complete object, 3, 3, 4, 3, is a tessellation of 4-dimensional Euclidean space. Now let us look at one vertex. Place a D4 lattice point at the origin. Around it are its 24 nearest neighbors. Those 24 points form a 24 cell. And this 24 cell is the vertex figure of the honeycomb. In other words, if we stand at one vertex of the 4-dimensional honeycomb and look at the cells surrounding us. Their local arrangement is encoded by a 24-cell. That gives us an important relationship. The 16-cell honeycomb has a 24-cell vertex figure. Now count the actual 4-dimensional cells meeting at the vertex. There are 24 16 cells, so 24 16 cells meet at every vertex. This number is not accidental. It is precisely reflected in the 24 vertices of the vertex figure. But there is an important point we must keep straight. The tetrahedra of the 16-cell are genuine 3-dimensional boundary cells of each 16 cell. They are not additional 4-dimensional cells filling the gaps between the 16 cells. The honeycomb is built from 16 cells alone. The tetrahedra appear as their 3-dimensional facets. This distinction will become important when we examine the structure more closely. At every vertex, the local counts are already remarkable. There are 24 edges, there are 96 triangular faces, and there are 96 tetrahedral 3-dimensional ridges. Yet the only genuine 4-dimensional cells are the 24 16 cells. So the hierarchy is 24 edges, 96 triangular faces, 96 tetrahedral ridges, 24 16 cells, all meeting around a single vertex. And at the center of this entire local structure sits the 24 cell. This gives us our first complete picture of the 4-dimensional honeycomb. The lattice supplies the vertices. The 16 cells fill the 4-dimensional space. Their tetrahedral facets meet to form the 3-dimensional boundaries. And the arrangement of the 24 neighboring cells around every vertex is encoded by the 24 cell. The picture is already far richer than the tetrahedral analogy with which we began. But there is still a question. We started this chapter by asking, how many directions are needed to organize the 4-dimensional structure? The 4 simplex suggested 5. The roots suggested 12. Now the 16-cell honeycomb gives us the geometric setting in which that question can finally be answered. To find those directions, we must look at the roots of D4 not merely as points, but as opposite pairs. And when the 24 roots are paired in this way, something remarkable happens. They become 12 distinct axes, 12 directions. The answer we have been looking for is beginning to emerge. The 16-cell honeycomb has given us something remarkable. It fills 4-dimensional space using just one type of 4-dimensional cell, the 16 cell. But when we look at the boundaries where neighboring 16 cells meet, something familiar appears. Tetrahedra. At first, this may seem surprising. After all, we have just said that the honeycomb contains only one genuine 4-dimensional cell type. So where do the tetrahedra come from? The answer is subtle. They are not additional 4-dimensional cells. They are the 3-dimensional facets of the 16 cells. And, more specifically, they are the shared boundaries between neighboring 16 cells. This is directly analogous to ordinary 3-dimensional space. A cubic honeycomb is made from cubes, but when 2 cubes touch, they share a square face. The square is not another 3-dimensional cell. It is the boundary between 2 cubes. The same idea is happening here. A 16 cell has 16 tetrahedral facets. Each one is a regular tetrahedron, and each tetrahedral facet is shared by exactly 2 neighboring 16 cells. So, the tetrahedron is a 3-dimensional ridge of the 4-dimensional honeycomb. It does not fill some leftover 4-dimensional gap. There is no gap. The 16 cells already fill the space completely. Now let us see how one of these tetrahedra can be constructed directly from the lattice. Begin at a lattice point. For simplicity, take the origin. O equals 0, 0, 0, 0. Around it are its 24 nearest neighbors. These are the 24 roots of D4. Choose 3 mutually compatible nearest neighbors. Together with the origin, they form 4 points, O, A, B, C. Now examine their pairwise distances. The distance from the origin to each selected neighbor is the same, and the distances between the 3 selected neighbors are also the same. Therefore, all 6 edges have equal length. The 4 points form a regular tetrahedron. So, a tetrahedron appears naturally inside the D4 geometry. It is not something we have added artificially. It is already encoded in the relationships between the nearest neighbor vectors. There is an elegant way to recognize which triples of roots produce these tetrahedra. Take 3 minimal vectors, v1, v2, v3. When their pairwise inner products share the same value, the 3 neighbors are mutually adjacent. Together with the lattice point at the center, they form a regular tetrahedron. And when we enumerate all such possibilities around a vertex, the number is 96. So, 96 tetrahedral ridges meet at every vertex. But remember what these 96 objects represent. They are not 96 additional 4-dimensional cells. They are the shared 3-dimensional boundaries of the 24 16 cells surrounding the vertex. Each tetrahedral ridge belongs to exactly 2 16 cells. This gives us the local structure, 24 16 cells, and 96 tetrahedral ridges around a single vertex. And the tetrahedra connect the 16 cells together. Choose one tetrahedral ridge. On one side is one 16 cell. On the other side is its neighboring 16 cell. The tetrahedron is their common boundary, so we can visualize the relationship as 16 cell, tetrahedron, 16 cell. This is the correct way to think about the tetrahedra in the honeycomb. They are the interfaces between neighboring 4-dimensional cells. And this distinction becomes important when we compare the 4-dimensional honeycomb with familiar 3-dimensional tessellations. In 3 dimensions, tetrahedra and octahedra can alternate to fill space. In 4 dimensions, something remarkable happens. The corresponding honeycomb closes perfectly with 16 cells alone. The tetrahedra do not need another roll. They simply form the boundaries through which the 16 cells meet. Now we can zoom in even further. Take one triangular face of one of these tetrahedral ridges. Exactly 3 16 cells meet around that triangular face. And take one edge, exactly 6 16 cells meet around that edge. So, the local incidence structure is becoming increasingly clear. At a vertex, 24 16 cells. At a triangular face, 3 16 cells. At an edge, 6 16 cells. And between neighboring 16 cells, shared tetrahedral ridges. The tetrahedra therefore provide the connective tissue of the honeycomb. They reveal how one 16 cell touches the next, and they give us a concrete 3-dimensional object that we can actually visualize and calculate with. So the picture is now: D4 lattice produces 24 nearest neighbors, which organize the 16-cell honeycomb, whose neighboring cells meet across regular tetrahedral ridges. The 4-dimensional cells fill the space. The tetrahedra describe their boundaries, and the D4 roots tell us exactly where those boundaries come from. In the next scene, we will step back from one tetrahedron and examine the entire incident structure around a vertex. How many edges? How many triangular faces? How many tetrahedral ridges? And how many 16 cells? The numbers will fit together in a remarkably precise way. We have seen how 16 cells meet across tetrahedral ridges. Now let's step back and count everything precisely around a single vertex of the honeycomb. Begin at the origin. Its 24 nearest neighbors are the 24 roots of D4. Each neighbor defines one edge of the honeycomb. So, 24 edges meet at the vertex. Now look at pairs of neighbors. When 2 roots have an inner product equal to 1, they are close enough to span a triangular face together with the vertex. Counting every such pair gives exactly 96. So, 96 triangular faces meet at the vertex. We have already met the next number. In the previous scene, we found that triples of mutually compatible roots form regular tetrahedra with the origin. There were exactly 96 such triples. So, 96 tetrahedral ridges meet at the vertex. And finally, 24 16 cells surround the vertex. Each one contributes its share of edges, faces, and ridges to this local structure. So the picture at a single vertex is 24 edges, 96 triangular faces, 96 tetrahedral ridges, 24 16 cells. Now let's zoom in further. Choose one triangular face. Exactly 3 16 cells meet around it. Choose one edge. Exactly 6 16 cells meet around it. And at the vertex itself, all 24 16 cells come together. These numbers are not arbitrary. They describe a shape you may already recognize. Take the 24 edges emanating from the vertex and connect their endpoints wherever two roots share an inner product of 1. What emerges is a four-dimensional solid. 24 vertices, 96 edges, 96 triangular faces, 24 cells. This is the 24 cell. The very same regular polytope we met earlier in this chapter, now appearing again as the vertex figure of the 16-cell honeycomb. Every vertex of the honeycomb carries its own 24 cell, describing exactly how the surrounding structure is organized. 24 edges, 96 faces, 96 ridges, 24 cells, all encoded in a single familiar shape. So the honeycomb's local structure is not just numbers. It is geometry we have already seen, repeating itself at every vertex, in every direction. In the next scene, we return to the question that opened this chapter. In 3 dimensions, 4 directions were enough. How many directions does 4-dimensional space actually need?